I'm Umeen Ransom. I lead a machine learning and software development team at Comcast. I'm joined by Nick Pinkernell, senior researcher at Comcast. We're going to talk about customer experience, model training automation, and a feature store problem. So on the agenda today, we'll talk about what we use as our use case, customer experience, when building out this machine learning platform, why data at scale is hard, and why we needed a feature store, and what we did to solve that feature store problem. So Comcast is a Fortune 50 company. It's one of the largest multi-service operators in North America. We have multiple lines of business, from high-speed internet, home automation, and of course our award-winning video platform, X1. There's a host of other products that we have, along with NBC Universal and Sky, and all of the products and services and media properties that come along with them. We are making customer experience our best product, and that's what we're here to talk about today, how we use machine learning to do that. So we have tens of millions of customers and hundreds of millions of devices on our network. So we have a lot of data, and we have a huge opportunity with big data and machine learning. So our machine learning lifecycle is not dissimilar to any other. We start with a use case, and foundational to any machine learning use case is data. Now, I mentioned we have billions of events that are generated by these hundreds of millions of devices and the customer base that we have. So we're using that data to train machine learning models to create predictions about customer experience. And it's an iterative process. We test the output, we make sure it's valuable, and when we do find that the model is producing the value that we need, we deploy it to production. We select the model and deploy it to production. This is not a trivial task. So handling data at this scale is challenging, and we need to make sure that we have a performant and reliable infrastructure that can serve this data to the models. We've chosen a Redis cache, and Nick will talk more about that later. So we use that to make the data available in production. And in production, these models are evaluated and monitored. We make sure that it's producing the right value, it's producing good predictions. But over time, all model predictions decay because features change and software changes. So we have to iterate on this process. Right. So what's our business problem? Comcast grew up as a cable company, and our customers like to call us for service, and they like us to interact with them on the phone, and when they have service issues, sometimes they like us to come to their homes. We call this a truck roll. This is when a service agent or a technician gets in a truck and goes to the home. That's why it's called a truck roll. So this is very costly. This is our operations that are very costly, and when we have inefficient processes in this operations, it produces waste, obviously, and that waste can cost us a lot of money. But we have a lot of data, and we have a lot of information about our customers. So we're using that data to create these machine learning models to help us understand our customer issues, create predictions about them, and help to bring them back to service. So our goal is to take this cost out of the business by driving those, that customer impact time down and driving higher KPIs. So we use these models to enhance our interactive voice response system and our chat agents to solve customer problems before they get escalated. And we use this data to prevent rework and, of course, prevent those very costly truck rolls that I mentioned earlier. So I'll take a quick poll. Has anyone heard of the $6 Million Man? Okay.
See, told you.
That's fine. That's fine, though. It's good for my analogy. So I'll give you enough information about him for anybody that doesn't know. So this is Steve Austin. He was a test pilot, and he flew an experimental aircraft. It was a horrible accident. He got hurt. But the cinematic science of the time was able to use machines to repair him, to make him stronger, faster, better. And that's what we're doing with our customer agents. We start with quality people who know our product, they know our customers, and we enhance them with technology. We deliver predictions and information to our customer service agents to upskill them so they can solve customer issues more quickly. So it's the marriage of machine learning, human empathy, and human decision-making to help make an overall better customer experience. So I want to dig a little bit more into this operations and the costs around these operations. So like I said earlier, we grew up as a cable company, and our customers like to interact with us through phone calls. A lot of times those calls are for understanding what's on their bill or general information about their service. But sometimes they have issues. So our interactive response system, our interactive voice response system in the past did a pretty good job of solving their problems. But when it fell short, it would get escalated to what we call a customer agent. And the customer agent would do their best to solve problems. And they didn't always have the best answers, and we would have what we call a truck roll. So truck rolls are really costly. Actually, they're 10 times as costly as talking to a service agent. And a lot of times, the truck rolls, they are successful. We bring the customer back online, their customer experience is good, and they're happy. But there are cases that we consider avoidable truck rolls. This is where we find that there's an issue somewhere in the network, and the truck roll would never solve this problem because we have to solve it somewhere in the stream. We also find that customers call us and they don't want us to come out to their house, mid truck roll. They decide they don't need a tech to come to the home. And then there are issues sometimes where we find that we get to the home and a simple reboot or replacing the batteries in the remote brings the customer back to service. These costs are we consider them avoidable truck rolls, avoidable costs. And we're using machine learning to help take those costs out of our system. We actually try to meet our customers at our digital edge with Xfinity Assistant. It's available on web, mobile, and X1. When customers engage with Xfinity Assistant, it immediately calls for a prediction based on the most relevant information about the customer. When we do find that there's a service issue with the customer, we send a prediction, we send a recommendation, and we send a button for them to press to restore their service. It also hosts a natural language processing chat agent where customers can interact and find out answers about their bill and other generic information. So now we have a machine learning powered service calls. Customers call in, and our IVR is enhanced with machine learning that has more automated solutions and helps to route calls more efficiently. When calls are escalated to our customer agents, they're enhanced. They have access to data and machine learning to help them understand customer issues. Overall, this helps to reduce the customer impact time and delight our customers more and drive down our costs around operations. And how are we doing this? Through machine learning at scale. So we process billions and billions of events. These events are the telemetry from the devices that make up the service chain that provide the experiences for internet and video customers. Throughout the day, hundreds of millions of records are updated that are available in our online feature store that are there to serve predictions for the tens of millions of customers that use Comcast video and internet products. So year to day, we've served millions of predictions. 60% of those predictions were for high-speed internet, and 40% were for video services. 85% of customers that use recommendations did not call back in a 24-hour period. This translates to millions and millions of dollars in operational cost savings. So with that, I want to transition to Nick here, who's going to tell you more about how we're able to do that.
Thanks, Mumin. So now that we've seen the customer experience kind of use case and why we need such a large scale for serving ML models, I'm going to go over a few things. I'm going to start off with the metadata and how we look up our metadata, how we look up our data sources, how we perform our feature engineering, and how we solve the feature store problem. We solved it, I'm just kidding, we didn't actually solve it, but we solved it for a couple use cases that are specific to what we were doing originally. However, they're general enough where folks should be able to apply them to their own problems as well in their own feature pipelines for their ML models. I'll then go over some model training, some model deployment, serving, and then a little bit of automation and how that all ties together. So in terms of feature engineering, though, there's a great quote here from the Quora forums, and the Shane Miel's answer to the question was, what is the intuitive explanation of feature engineering in machine learning? And his answer was wonderfully succinct. And it was, you have to turn your inputs into things the algorithm can understand. And as easy as that is to say, it's much harder to do in practice and at scale. But, that's what we need to do. So we start off with our researchers. These are the folks who are doing our research. They're looking at the data sources. They're looking at the features in our data sources that are the most interesting to them. They find one they like. They request a new feature source to be coupled up with our platform. So they'll make a request to our feature engineering controller, and that then makes a request to the schema registry. If it exists in the schema registry, and there's a specified schema for it, then we're able to build our stream object to serializers and then actually configure a consumer that will consume from that topic or stream, whatever it may be, Kafka or Kinesis or whatnot, and then actually start listening to that stream. But that's not all of it. We need more than that. And what we need to do is actually to do something with the data. This has been shown many different times and ways, but you have input data, which is essentially your X. You have some function you want to execute on that particular input data, and then you have your output, right? It's very simple in terms of displaying it. In terms of implementing this, though, it can get tricky. And you're like, okay, well, it's not that tricky. You do a one-hot encoding, or you do a label encoding, or something like that, or TF-IDF weighting, something. It's not that complicated. Where it gets complicated, though, is where we need to store history, or where we might need to aggregate or window the data. And that gets more difficult exponentially as you go up in scale. Right now, we're processing about 500,000 events a second. And we're even doing this with Python, believe it or not. And I'll explain a little bit about how we're doing that. So when we think of the input X, we're looking at systems like Kafka or Kinesis. We can even take HTTP requests. These could be in batch or individually. Batches over gRPC is pretty good. It's very performant. These could even be files from S3 or HDFS. So there's a lot of different inputs we can accept. For our function, normalization and transformation, those are fairly common, right? But the windowing and the aggregation, like I said before, that gets tricky. And you're probably all thinking, well, just use Spark or just use something else. Well, we do use those tools, but they don't provide as much operational insights as we kind of wanted early on. And we're slowly growing to support more tools and frameworks, but this particular example I'm going to show you doesn't use Spark. And then obviously your output is those engineered features, those features that are ready to be passed directly into your ML model. And that could be a classical model, a deep neural net, whatever it may be. So what is the feature store problem? Well, that's a good question. The answer is different for every organization. And it depends on whether your organization has clean data coming in, whether that data already has been aggregated or windowed, or whether you have a small amount of data or a large amount of data. So there was an earlier talk, and it was pretty good. It was about a system that they had built, and it was strictly serverless, but it was only 10, 20, 100, even 500,000 requests a day. Well, that's great, and AWS works amazingly for some of those use cases, small and large. But when you get to the very large, right, when you get to the 500,000 a second, 1 million a second, you need to think a little bit differently because those costs can become very high. So the feature store really is just a data store. You could pick and choose whatever you want here. You can use Redis or Cassandra. You could use Dynamo. Pick your poison. They're all difficult or simple depending on how large you need to grow those. So you need a feature store because researchers are really picky and really needy, right? They need their data and they want their features. And they not only want the original features, but they want the engineered features, and sometimes they even want the features on the intermediate steps, before aggregation, after aggregation, before TF-IDF weighting, whatever it is. And that's the problem. So our feature store, like I said, you can use Spark or Flink, you can use HDFS or HBase. We chose Redis here, specifically Redis cluster. I'll get into that in a minute. And we need to do a number of things to the data sets. So I'll start off with the research and model flow, and we'll work from the model backwards, right? So what our researchers do is we're a pretty big Databricks shop, which makes it easy because we have a lot of data in S3, but we also have a lot of data in HDFS and legacy SQL databases internally. So there's a lot of data sources, but luckily we're starting to standardize on some of our data ingestion and pipelines. So once our folks get their data into Databricks, and then they start working with it and they find something interesting that's going to solve part of our customer experience use case, they will train a model. And once they train their model, they're going to push their Python code to GitHub from Databricks. There's a synchronization method there. And once it lands into GitHub, we have GitHub hooks for automatic deployment with Argo CD. Now, who here has even heard of Argo CD? Yeah, a couple, right? Who here's heard of Kubeflow? A bit more. And obviously, who here has heard of Kubernetes? And yeah, most folks, right? So if you haven't checked out Kubeflow, or in particular Selden Core is a fantastic project. We use it a lot actually for production model serving, and it's within Kubeflow, or you can install it separately. Argo also works really well in the Kubernetes ecosystem, so that you can have YAML or JSON-defined configuration, and that configuration can be automated. And then we just, Argo picks that up, it picks up that YAML, it builds a Docker image, pushes it to our Docker Hub repository, and then does a kube control apply, essentially. There's a little bit more to it, but if you get down to it, it's just deploying that configuration. So looking at a very simple example of how some of our researchers train an experiment or a run with Databricks, and more specifically with MLflow. The reason we choose MLflow here is because it gives us a couple nice things. It gives us experiment and run tracking. It also gives us a standardized package format so that we can do standardized things to those trained models. And in this specific example, this is Python code, and we're looking at just a simple experiment. And what we're doing is we're actually doing the predict, evaluating our metrics here, and then we're logging some parameters to that MLflow output so that we can look at these historically. And MLflow has a GUI as well that we can check out. We also get to name this particular run or experiment, and we can even iterate over these with different hyperparameters. We can log different evaluation metrics from those particular training experiments or runs. So it's pretty nice and flexible, and it gives us a standard format. It can also produce MLeap models as well, which are nice, as well as the ones you're all used to, Pickle and TensorFlow, those sorts of things. This specific example here is just a visualization of 4 experiment runs with MLflow, just to give you kind of a feel for how it looks. And specifically, this is within Databricks, so you can see the Databricks menus on the left-hand side, but the particular values aren't super important. It's just to show you that you can iterate over these, you can run a dozen or hundreds of experiments with MLflow and kind of track your utilization of your particular metrics there. And a little bit of visualization. They're adding a lot more to it. It's a nice tool. So that's how our folks train their models and how we actually produce our model artifacts. How we serve our models is deceptively simple. And when I say deceptively simple, it really is that predict function in Python. And going back to it, we are running Python in production. We let our researchers deploy their own models in prod. We have to horizontally scale those a lot, obviously, because Python is single-threaded due to the global interpreter lock. I didn't feel like writing a bunch of multi-threaded Python to support that, but we just spin up more containers and make our Kubernetes clusters a little bit bigger, except for some of our extreme use cases. So that predict function right there, and this, the code I'm actually showing you is on GitHub. We got access to open source this. This is a demo I did earlier in the year, so I'll give you the link at the end. And that predict is just running a simple sklearn predict on a pickle model. So that model was persisted as an artifact via the pickle format, and then we can just invoke that. And that predict method is actually exposed via HTTP and gRPC with Selden core. So it makes it really nice. And then you gain all sorts of wonderful things with Kubernetes, load balancing, and a bunch of great stuff for your model endpoints. But even though we can invoke that with Kubeflow, right, via HTTP, we can also do this with a number of different methods. As a part of a chain, if you wanted to kind of construct your own ensemble, or we can actually directly invoke this because it's just code. We can make a library out of this. We can include this in other code as part of our consumer, and you'll see that in a minute. That's kind of how we accomplish the streaming bit. So in our pipeline automation, though, digging a little bit deeper into that first metadata piece, once they get their data source and they really like it, we actually have to do a number of things. So we create multi-step workflows in Argo, which automatically deploy. They do the kube control apply at the end. So it pretty much just details out what we've been talking about so far, which is building those object deserializers. Now, if you have a schema registry and you're using a nice language such as Java or something that really supports, your schema registry or Confluent or Apache Atlas, all of those things, you might not need to actually build those object deserializers, but for some of our programming languages, we do. It will then automatically build the Docker image. It will push it to the Docker hub, generate the deployment. There are hooks out to Git and our Jira systems as well, and then it will run the deploy. And we also have tagging and versioning, those sorts of things. I didn't detail that out here, but that's part of the flow. So bringing it all together is really where we look at how we can invoke these pipelines, right? And as part of the feature store problem, you'll see it as an entire end-to-end solution. This particular diagram shows somebody else doing the heavy lifting. And this is kind of your win-win scenario, right? You have another team within your organization, and that external system there, they're producing the features or they're listening to those particular features. They're doing the aggregation, they're doing the heavy lifting on the features, and they're also doing the parsing and deserialization and whatever they need to do, and then they're just making a REST or a gRPC call to your Selden endpoint. And this is wonderful because all you have to do is stand up a Kubernetes instance, install Kubeflow, and off you go. And you can empower your researchers to just get their models out there as quickly as they can do a kube control apply. The nice thing is there's no downtime on a lot of those deployments, and that's really good. The other nice thing about this particular scenario is you don't have to deal with a feature store. with historical data and all of the complexities that come out of that. But inevitably, you probably need to deal with history at some point or another. And it's going to look a little bit more crazy here. So if you take in some of that raw features into your system, right? If an external system or team isn't doing this for you, then you need to listen to those streams or topics directly. You need to write some sort of consumer pod, which we showed a little bit earlier, but you could also manually write it yourself. And you need to listen to that Kafka topic or that Kinesis stream or whatever it is. And when you consume that, you also need to perform the deserialization of that particular data source from your schema registry. But here's where the feature store comes in. We're able to do Redis, and this is our particular implementation right now. We do gets and sets to Redis, and we do many millions of those a minute. And we use hashes in Redis. Sometimes we'll use lists or sets in Redis, but the majority of them are just simple gets and sets. And even deeper into how we do that is we just create JSON objects and then gzip compress them. It's a really nice way to kind of just stuff things in Redis if you're not using one of the actual Redis data structures. But then we needed a way to get the engineered features to the model, because that Kafka consumer pod is separate from the actual model itself, right? We could invoke the model from there. We definitely can. But it's nice to have a little bit of a back pressure mechanism, to have an additional pub sub mechanism so that our model can be invoked at a different rate, so that we can use Redis streams as a fan out mechanism, so that we can actually call all of those Python containers I was talking about earlier. Right now, I think we have about 30 or 40 Python containers, pods, running for a single model at the moment, and that's one of our more high volume ones. But they're all single threaded, so we need to horizontally scale those. So with Redis streams, we just do an xadd, and if you haven't played with Redis streams, it's real similar to a Kafka append-only log, right? But some of the implementation and semantics are a bit different. But that allows us to have a separate feature consumer, and that separate feature consumer can keep up with the model as it needs to. So it can directly invoke that model, or your feature consumer could even call the Seldon endpoint if you wanted to. We get a lot of benefits out of using Seldon. It has Grafana and Prometheus built into it. So if you invoke the model directly like we've done here, you have to build some of those metrics into that feature consumer. But a lot of you are probably, might be asking, Redis is small and memory is small, and we might need to store terabytes of data in an intermediate cache, right? So all you need to do is either add more Redis instances, horizontally scale your Redis cluster. Using an individual Redis instance, you're limited by the RAM of the particular instance. So if you're using EC2, that's like 320 gig on a 24x large. But if you're using Redis cluster, you can horizontally scale that with the masters and the replicas, or the slaves. So the nice thing is if you have a particularly large data set coming in, such as raw feature set A, you might actually use just a dedicated Redis instance just for that data set, which is nice. And then you can continue to have more or less the same architecture that we've had with our previous data sets. So here's the code, as I promised. You all can check that out. I think it's the first one on there. It's the end-to-end ML feature streaming with Kubeflow, Kafka, and Redis. And in that code, all of the example code is there, and it's all written in Python, so folks who are used to that can take a look at that. All of the JSON and YAML configuration is there with Seldon Core and Kubeflow, as is some documentation. That's all we have for today. Thank you very much.
Awesome. So I'm going to pass around the mic for questions.
Hi, thanks for the talk.
Yeah.
how do you verify when the model is in production, whether the features that you produced offline and you're ingesting online are in parity? Meaning they are exactly
Can
the
you
same.
ask again? I'm sorry.
So let's say you have a feature produced offline. Data scientists spent 2 weeks on it. It's a Windows feature, heavy data.
Yep.
Train a model, certain quality came out, and then the person goes to production. This pipeline kicks in for
Yep.
online. Do you have something that measures continuously if the features that are ingested online are the same as you would have gotten if you would reproduce it offline?
I see. So you mean like feature drift from the batch features they use to train their models initially?
No, more checking whether the completely different code base offline and a completely different code base online semantically result in the same.
Oh, I see. Right. So we do checksumming on the model artifacts, and we also use just GitHub tagging for releases. So, I mean, the checksumming on the particular artifact verifies that the model's the same, but the features may not be the same because there might be a difference there or a delta between the data they use to train the model and the actual data coming in production. So we have to measure and monitor that. So I'm sorry if that didn't get the whole question, yeah.
Hi, my name is Dominic. So how do you optimize feature building from a complexity perspective? For example, right, let's say you're trying to identify multi-dwelling units.
Sure.
Right, so multiple. So there's a number, if you look at the address, right, they might have different numbers, right?
Yep.
You know, 1 Main Street and 3 Main Street might be the same building, but it gave them 2 numbers, right? I mean, for a role, it's going to be important to know something like that it's the same building, right? So there are a couple ways to do it, right? So, but it's going to involve a combination of multiple fields. So I got to look at geocode, I got to look at location, I've got to look at address, and put them all together to make one, right? So when you're working with your data scientist, you can either build one complex feature or a feature that requires a lot of complexity by taking in 3 different parameters, making sure they don't match any other of those 3 different parameters anywhere else.
Yep.
And then say, yep, this is a multi-dwelling unit or not. Or you divide it into 2 workloads. You create 2 features and have the data scientists use 2. One that says this is the same longitude, latitude as another place,
Right.
and this is an address which is different. But because they're the same, they should be 1. How are you working that sort of optimization into feature engineering?
Right, sure. So luckily, we have an is MDU Boolean, right? If we didn't have that, then we'd have to use the logic of the producer. But that's an interesting question because when we go to train our models, we need to take that Boolean into account. And some of our models, actually, we have 2 different models because the telemetry is so different between the 2 data sets, right? You know, a residential neighborhood acts completely differently than a multi-dwelling unit. So in certain cases we have 2 models, and in some cases we have 1, and we let the complexities of the neural network tease out some of that interplay between the features.
So, I mean, based on your answer, it means that you really are doing 2-phase processing, right?
We are.
One way or another, you're already figuring out it's an MDU.
Right.
And then you're creating, so, it's not another feature, but it's at least you're pre-processing the data to make it look so it can support a series of features that will require that information.
Exactly. And yeah, they actually do that based on like a dwelling ID, which we get from, I think, the city records, but I'm not exactly sure where that data comes from.
Hi, great talk. Thanks for sharing. I'm curious, we use mostly batch processing right now. We're starting to look at streaming, but do you think that the architecture you described could be largely transferable?
Yeah, I don't see why not, because if you get a batch of requests in, and let's say that's only every 5 minutes, then you can still make a large gRPC request to that Celdent endpoint, or you can still process that as a message over Kafka or whatever pub/sub mechanism. Yeah, for sure.
Hi, here. You are using Kubeflow and Kubernetes. Did you consider, Google has this product called Feast, as a feature store product. Did you consider using it or did you try it out?
We have not tried it out yet. In fact, we're looking at many things because this is kind of our version 1. Okay. Our version 0 actually used Flink and a number of other things. Okay. And we had a number of challenges there with scale. So we implemented this as our V1. And then our V2, we're actually going to allow for many methods of feature streaming. You know, Airflow. I don't know if you've heard of something called Dask. But yeah, Dask is pretty sweet for Python. It's a pub/sub mechanism. We're also looking at, you know, Kubeflow pipelines for some of the models as well, but that doesn't help with feature streaming. So we're trying to take a lot of that into consideration. That's an interesting one.
Thank you very much. I
Yeah.
learned a lot. Thank you for sharing. Internally, we have looked at Kubeflow and Selden. One of the issues that we raised was, first of all, Selden's not really optimal for batch, and that goes back to the gentleman's question. But that's not my question. The real question is Kubeflow. We're finding, our perception is it's not ready, and I'd love to know your thoughts. The reason is that the data scientist has to do a lot of configuration, a lot of YAML code. To push into Selden requires changing YAML. You need to also, everyone needs to have cluster admin. You're not a data scientist, you're an engineer.
Yeah.
So what have you done about that, or does the data scientist have to be an engineer in your world?
So there doesn't, and it's not in this talk. I did an earlier talk at Spark AI this year, and if you want to check out the slides, there's a specific slide on how we automated that whole piece. And it goes into how we programmatically generate the YAML for those folks and then actually do the kube control apply for them. So all they have to do is commit their code to Git, which is pretty nice. Because yeah, it's difficult. We've had a number of our researchers say, well, I want something very complex in terms of a Selden graph. And I'm like, well, there's no getting around writing your complex graph, but at least you don't have to generate all the YAML every time. And we're slowly working to automate that. Yep.
Any other questions? All right, you could come up to them after to ask your questions, but
Thank
thanks
you.
again.
Thank you.
Thank you.